All right, hello everybody. We're gonna go ahead and dive in because last time we were here, we didn't quite manage to finish up unary operations. And so we are gonna be trying to do that. I'm sorry, we couldn't see today's topics up here. Okay, so these are today's topics. First things first, we're gonna finish up those unary operations. We're gonna talk about compile time versus runtime. We're gonna talk again about compilers versus interpreters. We're gonna talk about how we persuade ourselves that our compiler is correct. And then we're going to talk a bit about Booleans. I think we'll probably add them into the interpreter today if all goes well. Probably not into the compiler. Okay, so here we are. We've been thinking about, before I dive in on content. Quick reminder, even on weeks when there are no homework/programming projects due, there are still drills. Please still fill in the drills so that we know how y'all are feeling about all the various topics so we can make sure that everyone's on the same page. Okay. So now let's finish up that task that we had started. And we had decided some things about how we wanted to actually implement unary operators. So in particular, we had decided about the outputs. Hopefully the outputs are uncontroversial. But we had also decided some things about what would or would not be satisfying implementations. And I want to remind ourselves that one of the things we decided would not be satisfying was if we just went ahead and tried to do this computation at compile time, and then just popped the answer associated with doing that computation, if we just popped that into the compiled code directly. And the reason we decided that wasn't okay was because we might eventually want to take some input, right? Maybe we were going to go ahead and read something from a file, or we were going to ask the user to type some input. And if we were going to be getting some input, then we knew we would be in trouble if we were trying to pre-compute everything and we had no way to actually have the assembly itself do the addition. And so I'm going to run us through a visualization that we are going to see a number of times over the course of the semester of what is happening on our machines when we are running our assembly. And this will basically be a picture that we draw that is going to get increasingly complicated as we understand more and more about what our processor is doing. But for now, we have a quite simple one, but I still want to just talk us through what's happening when we run this assembly, which is the assembly that we actually want to emit in order to implement the program that we talked about up here of add 150. And you can see that if you take a look at this assembly, it sure looks as though what it's doing is coming up with 50 and then doing the addition right there. And we'll find out that that is, in fact, exactly what's happening. So the first thing that happens is we see a label. That turns out not an instruction. We don't have to do anything, right? That's not something that actually goes to the processor. That's something that we're using as sort of a little helper for ourselves. And we will eventually figure out how we can use it to jump to the line that comes after, which is, in fact, an instruction. So what happens when we run this instruction? Well, the only thing that happens is we come up with the value 50, and we decide to put it inside the register RAX. So I'm going to go ahead and write that like this. Inside RAX right now, we have the value 50. And now, if we go on to that next instruction right here, we can see, OK, all we're going to do is replace whatever is in RAX right now with whatever was in RAX plus 1, which is to say the value 51. And then we go ahead and we actually return control to whatever called us, which in this case is going to be our C runtime. Feeling pretty comfy about this assembly? Amazing. Let's make sure that our compiler can actually emit it. So let's turn back to our compiler. Oops. Let's plug in my laptop to the projector so that we can see where we were with our compiler. Lovely. OK, so we left it in a little bit of a weird spot, actually. So we can take a look here and see that we had figured out this sort of wrapper function that we were going to want. The reason we decided we wanted this wrapper function was because we figured out that if we started trying to have the num case here and then the add one case, we were going to end up having this repetitive boilerplate, which was going to get in the way of some of the things we were doing. And so we decided, OK, let's extract that boilerplate out. Let's put that in this little compile helper function. And what we'll have in here is some of the same things that you'll see, right? We have that global entry thing, we have that label entry thing, and we have that thing that is actually returning control to the runtime. But then in the middle, what we're doing is actually pretty simple. We're just making this call to compile exp. And what we will expect compile exp to do is make sure that whatever assembly is going to put the answer associated with evaluating our program, whatever assembly is going to get that value inside RAX, had better come from a call to compile exp. So let's go ahead and fix up what we've got in here. Let's ignore add one for a moment, because we're not still totally sure what to do there. But we're pretty sure what to do with a number. So let's go ahead and remove the parts of this that we no longer need, right? We're no longer putting the boilerplate right here. We just need to go ahead and move that immediate value into RAX. And in fact, we no longer need to do the string concatenation stuff because all of that is being handled out here at compile. So okay, we now have what we want inside that little helper for handling numbers. But of course, the reason we were doing all this transformation, the reason we started working with our nice representations of assembly, but also our nice representations of S expressions, which do turn out to be for symbolic expressions, that is what the S stands for. The reason we were doing all of that was so that we could have sort of nicer stuff happening in here, which would make it easier for us to write the next thing. So let's go ahead and extend to that. Let's do list sim add 1. And what I want you to do is discuss with the folks nearby, what do we want to have on this next line, right? When we are handling an add 1 expression, what is the assembly that we want to emit? Go ahead and discuss for about a minute. All right, so I'm going to ask you to hum this line that I've put in here that says add 1 to whatever is in RAX right now. Is that going to be sufficient? Hum if you think that's it, we're done. Hum if you think not so much. Yeah, I totally agree, right? So we had first better make sure that whatever's in RAX right now represents the argument, right? We haven't used arg, and in fact, OCaml's even warning us that we haven't used arg. So what could we do to make sure that the value that is associated with evaluating arg is getting put in RAX? Go ahead and discuss for 20 seconds with folks nearby. All right, I'm hearing the answer that I hope to hear, which is we actually already have something whose role is to put the value of a particular expression inside RAX. We already have something, and that is compilex. So if we go ahead and just make our recursive call here on arg, that is going to make sure that the value associated with actually evaluating arg, that it is going to emit the assembly instructions that are in charge of putting that value inside RAX. So let's first go ahead and make sure OCaml knows we're allowed to call this recursively, and then let's go ahead and do our list concatenation to make sure that whatever comes out of this call gets mashed together with this addition, and we'll be good to go. Are there questions about this? We feel good about our recursive call. Amazing. Okay, so now I think we're probably all going to be able to guess what sub1 is going to look like. So let's go ahead and do that real quick. And then let's make sure that this actually worked for us. So let's do utop. We will open our compiler, and let's compile and run. Add 1. Hey, our programming language has been extended. It is no longer just numbers. We can do computation. So here we go. We can, oops, I've mixed it up with sub1. Let's make sure that I actually saved the file after doing that. So let's do, oh, that's how I mixed it up. I added too many parentheses. Okay, great. So we can go ahead and have these nested calls. That's all fine. That's totally fine. Any questions about how we have implemented addition and subtraction here? Our first add one, sub one unary operation. Yes?
So right now I guess, yeah, we're only working with the add one and sub one. We're always assuming like our base case that like the last thing we're coming across is a number.
Oh, I love this. So this is something we're going to be reflecting on later in the class session. What kinds of values do we have access to right now? Can we have anything other than numbers as the type of the values that we are actually manipulating in our programming language? Yeah, I agree. So the only thing we've got right now is numbers. So we don't have to do anything presently to check if we've got a number coming in. But if you remember the slide that I showed at the beginning of class, we might have something coming in soon. Okay, amazing. So let's go ahead and step back for a moment. I'm going to bring us back to our whiteboard, and I'm going to have us reflect for a bit on basically what we mean when we're talking about a compiler versus an interpreter, because we're about to complicate our story a little bit. So we have these three columns on this diagram. I'm sorry, three columns, I mean, because we have sort of this thing on the, oops, this thing on the, pen's not working. Okay. There's the thing on the left of this line, that's the first column. There's the thing in the middle, and then there's the thing on the right. So everything that's inside the blue box represents the things we have to do in order to use a compiler to get a value associated with the program, right? Everything that we see on the right side is what we have to do in order to use an interpreter to get the value associated with the program. And so what I want us to think about right now is actually a couple things. I want us to think about basically, what is happening when we use these? So I'm going to turn to, yeah, let's actually turn to this slide. And what I want you to do is come up with someone nearby, when we are talking about each of these three columns, is the stuff that is happening in that column happening at compile time or at runtime? Now, we've talked about these phrases a little bit a couple times now, but always sort of in passing. And so now I want to say that they mean exactly what the names sound like, right? Compile time is the time that we are compiling a thing. Runtime is the time that we are running the thing. And we are going to use the terms static and dynamic also to talk about these. So if we are describing something as static, that is almost universally going to mean that we are talking about something that is happening at compile time. If we use the term dynamic, that is almost always going to mean something that is happening at runtime. And so what I want you to go ahead and discuss with folks nearby for each of these three columns is this process, the thing that is depicted in the column, is that happening at compile time or at runtime? Go ahead and discuss. All right, so let's go ahead and decide. For this column right here, do we think this is happening at compile time, hum for compile time? Hum for runtime. Yeah, I totally agree, right? This is compilation. It says it right in the name. At this point, when we are using the compiler, we're using it to pop out a program, that is compile time. What about this middle column? Do we think that this is compile time, hum for compile time? Hum for runtime. I totally agree. And so this is one of the things that's so weird about using a compiler, right? Is at this point, we have a representation of the program that we are trying to run, and we could throw away every copy of our compiler, right? We can just toss that in the trash, stomp on it, destroy them all. We might not have that compiler anymore, and we could still run this program. And that's totally fine, because we now have the representation of everything we need in order to run that program. It doesn't have to interact with the compiler at all. We've got the representation that we are going to use. OK. And now, onto this third column. Do we think this is happening at compile time? Hum for compile time. Hum for runtime. Yeah, I agree, right? At this stage, we are actually running this program. But this is a little bit kind of mind-bendy, right? Because surely, at some point, the processor has to come into play, which means something must have made those ones and zeros. Where did those ones and zeros come from? How did we get those ones and zeros? How did we manage to even get out this value 42 if not by using the processor, or if not by somehow having a compiler in the mix that produced something that we could send to the processor? And so that's what I want us to wrestle with for a moment. If you have a piece of paper, go ahead and pull out your piece of paper. If you don't have a piece of paper, just jot some notes to yourselves about what we think is going to be in this orange box. But I'm going to explain what we're thinking about here. Right? So I've sort of broken open what's happening inside the compiler versus what's happening inside an interpreter. And I'm going to sort of talk us through the stages bit by bit. And then I'm going to ask you to try to come up with what's going to happen inside the interpreter. So here we go. We've got a program written in 164 lang, right? Our little scheme that we're making. It is written there. And that is one of the inputs along with this file we have written, compile.ml, right? That is just an OCaml program, right? So we wrote some OCaml inside compile.ml, and we fed that along with this program in the programming language that we are inventing. We fed both of those into the OCaml compiler. The OCaml compiler says, OK, I can take these inputs, and I can actually use that to produce some assembly. We've seen it appear inside program.s, right? And then that assembly that we see inside program.s, we can do various transformations to come up with machine code. And then we can pass that machine code off to your x86 processor of choice. And out we get this nice little answer 42, right? So that's how we go from a program to a value in compiler land when we are using a compiler. So this, I think, makes it pretty clear where we are getting that assembly that we're eventually running, right? In some ways, it's a little bit wacky because it does seem like the OCaml compiler is involved somehow. But ultimately, we know that this program that we wrote, compile.ml, is emitting assembly. And that's the stuff that's eventually going to actually run on the x86 processor. So I think it's kind of clear where the ones and zeros are coming from here. Yes?
Is that also happening when we use utop to simulate basically the execution? Is that through the OCaml compiler, or is it directly sending the assembly from compile.ml to the processor and spinning on the other?
Great question. So this question is about our compile and run helper, where we have sort of pulled together both the process of doing compilation and the process of running. And that is exactly the process that we're showing right here, right? So when we see that we're first running the compiler, and then we're going ahead and immediately running the program using the computer's processor, that's sort of talking about both the compile time process and the runtime process. So this whole process, right, getting to the machine code, that is, let me actually use a thing to point to this, right? This is all happening at compile time. This is all happening at runtime. We can choose to just go ahead and run those in sequence. And that's what's happening inside compile and run, our helper function. But yes, everything about this image is exactly what's happening when we use compile and run. So does anyone have any questions about where those ones and zeros are coming in? Like we're all like pretty sure that they're probably inside here. Hopefully we're pretty sure about that. Okay, great. So now I want you to focus with someone nearby on what's going to happen inside this orange box, right? I'll draw us one of the boxes inside here. So we're going to have an OCaml program called interp.ml, right? That's going to be one of the things involved. We'll have that box inside. Where are we getting the ones and zeros? Fill in the rest of this box so that it's clear where we're getting the ones and zeros. All right, so we're starting to quiet down. So I'm going to start talking through the pieces that are happening here, right? So we've got this OCaml compiler. If we think about what the OCaml compiler is doing, it is in charge of figuring out how to turn a program, an OCaml program, into ones and zeros, right? And so when it gets as input this OCaml program, right? Interp.ml, we are like in our heads, when we are writing our interpreter for our scheme, we're like, this file that I'm writing, this is the interpreter. But from the perspective of the OCaml compiler, that's just another OCaml program. It knows how to turn OCaml programs into ones and zeros. So when we get in interp.ml as one of our inputs, and we also get this sort of input that's taken into the program itself, we can go ahead and turn that into the ones and zeros, some machine code, that then we get to run on the computer's processor. And that's totally fine, right? It is OCaml, the implementation of OCaml, however that was implemented, that has to figure out how to turn this OCaml program into a bunch of ones and zeros. And from the perspective of OCaml, this sort of interp.ml program we have, it doesn't care what it is. It doesn't care that we are seeing that as an interpreter. From its perspective, one more OCaml program, no problem. So do we feel, yes?
So the interpreter just passes the input into the OCaml file itself, whereas the compiler that we're writing just spits out the machine code.
I love this, right? So if we think back to when we were talking on that very first day about what is the type of a compiler, what is the type of an interpreter, we said, okay, the type of a compiler is some input program to some output program, right? That's sort of what's happening. We're getting a program in, and we're getting a program out. The interpreter, on the other hand, is taking a program as input. I'm sorry, I'm gesturing the wrong way for y'all. It's taking a program as input, and then a value is coming out the other side. And so that will be the role of our interpreter. It is supposed to go ahead and calculate, analyze this program that it's getting as input, and just pop out the value associated with running it. Make sense? Yeah, It is a little mind-bending. We have other, yeah?
If the point of the linker in the beginning, when we first thought of it was because of memory constraints, do we still need to do all that breaking up and putting it back together, given we have better hardware?
The linker is just to make sure that the different parts of our program can talk to each other, right? So by default, our little C program, right, that we've actually used to make the runtime, it has its assembly that's generated. We have our assembly that we've generated. We just have to make sure that those two can talk to each other. That's all we're using the linker for.
Could we one-shot compiling a single file, or is it just are there actual?
Oh, I love this question.
Are there actual benefits to doing this whole process?
So I think this question, well, okay. I might not understand this question. I'll answer the question I think you're asking. So I think the question is, do we need to have the runtime? What if we just generated all of the assembly ourselves? That way it would already know how to talk to itself, and we could just run that. And that would be totally fine, right? There are some things that are really, really annoying to directly implement in assembly. And if we don't care about having low-level control over how those things are implemented, it makes more sense to put them in the runtime, right? If we don't care about being able to really explicitly control the particular assembly that's going to get emitted for this thing, we usually pop that in the runtime. And so for that reason, it is useful to go ahead and have these two separate components that we then link together. But it's not really a big deal, right? This sort of linking process is very easy and mechanical, and not a huge, yeah. Yeah?
So is interpreter not hardware agnostic? Does it need to know the specs of machine that you're running your interpreter on?
I love this question. So this question was, this interpreter, we're thinking of it now as just being an OCaml program. Does it need to know what hardware you're going to be running on? And the answer is basically no, right? Assuming our OCaml compiler, or whatever it is that we're using to actually implement our language, assuming that that tool that we are using in order to get the ones and zeros can make the ones and zeros for whatever processor we're actually going to run it on, we're good, right? We don't have to have specialized the interpreter for x86 the way we are specializing our compiler for x86. So yes, it can be agnostic to what it's going to be running on, as long as the program that we are actually using to compile it, right? Because there's a compiler that's going ahead and feeding it in, right? As long as that tool can figure out how to run it on the hardware we're targeting. Yeah? Oh, I love this question. So this question is, could we actually sort of hook these up together, right? Say I want to go ahead and implement my, my little scheme by writing something that compiles it to Python. And then the Python interpreter is going to run. Well, the Python interpreter was written in some other language. And so that language, right, whatever was actually used to write my Python interpreter, that's the thing that's going to be in charge of producing the ones and zeros there. Absolutely. Is that the question? Yeah, we can do all kinds of ways of linking this together. We can put compilers and interpreters in all kinds of sequences, and it's totally fine. Now, recall that the interpreter, its goal is to actually produce the value. And so in some ways, that's supposed to sort of bottom it out. But the thing that actually produces the ones and zeros for getting that value out of the processor, right, that can be doing all kinds of things. Yeah.
So when should you use a compiler versus an interpreter?
I love this question. When should we use a compiler versus an interpreter? There's sort of the first draft answer of this, which is, in general, because you get low-level control over the assembly that you're emitting, or the low-level language that you're emitting, you don't have to emit assembly when you're writing a compiler. Because you get a lot of control over exactly how the program is going to run, there are some performance benefits to implementing your language as the compiler. Now, on the other hand, it is usually a lot harder to reason about a compiler than to reason about an interpreter. This is not universally true, but this is often true. And so often, if you are looking for something that you can pick up really quickly and you can really quickly make an implementation for a language, you might be looking at an interpreter. If you are looking at, I want to make something that's going to be super high performance, you might be looking for a compiler. But this is not a hard and fast rule, right? So you can absolutely make interpreters that are very performant. Something that came up the other day was this idea of just-in-time compilation, and that we can figure out that this part of our program is being run a lot, and so we can do some compilation inside the interpreter. So there are things we can do to make interpreters fast. There are things we can do to make compilers easy to reason about. And so this is sort of a general guide for when we're reaching for these, but basically one of the goals of this class is you will understand more about the trade-offs between these by actually implementing them. So you will have a much better instinct for when you want to reach for one versus the other by the end of this class.
Does it also have to do with syntax as well? Like Python has been syntax compared to C.
Oh, very interesting question. So does it have to do with the syntax? So no, right? We can invent a compiler and an interpreter for the exact same language. Nothing stops us from doing that.
But like,
Is one harder than the other?
when we're just talking about syntax.
Bless you. So is a particular kind of syntax going to be harder for a compiler versus an interpreter, or harder for an interpreter versus a
I guess
compiler?
as someone to write, when you is it better to just compile everything within another compiler and then an interpreter, or like like what is there a reason why Python is using C as its compiler instead of just writing it as like Python says it has?
Oh, this question might be about what language should we use to implement an interpreter, what language should we use to implement a compiler. Yeah, so all of the same stuff that we have talked about in the context of why we have used OCaml for this class, it's all the same deal, right? So like, if we care about the compiler itself running really quickly, maybe we would actually choose a language that we know is going to run fast, right? Like it is implemented in such a way that the programs that we write in it are going to be efficient. So if the compiler speed itself, not the output program speed, but if the compiler speed matters, we might choose a language that we know is going to be very fast. In general, mostly we're picking based on what is going to help us write the particular kinds of programs that we need to write, right? It's sort of the same way we choose a language for any kind of program that we're writing. It's like, do we think it's going to make it easy to create a program that has the characteristics we want it to have? Okay, so now we have wrestled with how we can use an interpreter, even though the interpreter is not necessarily going to be popping out something that is visibly assembly instructions, right? We are not going to see that assembly representation of the program ourselves. And I now want us to turn to something a little bit different. So I want us to, it's going to seem like a left turn, I promise it's going to connect. I want us to talk about how we can persuade ourselves that our compiler is correct. So I'm going to turn us for a moment back to the compiler that we just looked at. And what I did to try to persuade all of you that this compiler was correct is I ran these programs, right? I ran add one sub 143, I ran add one sub 143, and I was like, look, it's doing the right thing. Don't you all believe me that it is correct? And so what I would like you to do right now is hum if you think that this is persuasive. Hum if you think this is not so persuasive. Absolutely. I love this skepticism, right? If GCC was like, yeah, we tried out a couple programs, the new version looks fine, like we would probably not be feeling super comfortable with that. We like to think that our compilers are being evaluated, validated, checked more thoroughly than that. And this makes a lot of sense because errors in the context of a programming language implementation are super high stakes, right? In the worst case, a bug that we have left in our programming language interpretation, whether that's a compiler, whether that's an interpreter, can actually end up introducing bugs into all of the programs it is used to compile or interpret. And that's a really bad outcome, right? Sometimes this means planes crashing, sometimes this means, I don't know, websites going down and people losing a lot of money. The various ramifications can change, but we have some reason to think that programs are kind of doing stuff out in our world that matter, and that introducing bugs in them is bad. And again, if a compiler or an interpreter is introducing them, if a language implementation is introducing them, it can potentially be putting bugs into all the programs written with that language. So I want you to discuss with folks nearby for about 2 minutes. What should we be doing to persuade ourselves that this compiler or any compiler is correct? All right. I want you to start yelling stuff out. What do we got?
Checking against like another compiler.
Ooh, checking against another language implementation. Love that.
Formal verification.
I'm hearing formal verification. I was expecting that from this area of the classroom. Yeah, absolutely. Formal verification. I love it. Testing, yeah, absolutely, right? We often, when we think about trying to persuade ourselves that our software is correct, we're often thinking about testing. Okay, cool. So that's giving us some strategies. I'm going to talk us through these strategies and what might be the pros and cons of them, right? So I think testing is a supernatural version of sort of the first instinct, right? So we can do basically the automated version of what I was doing up here when I ran things on a couple examples. We can write unit tests for individual elements of the compiler. We can write a particular program, run the assembly output, and say that we expect a particular value, right? So that's all good. Compilers are interesting because there are actually these two different ways for us to think about what it means for the compiler to be correct. We can think about actually examining the program that comes out the other end, or we can think about running the program that comes out the other end. Both of those could be interesting ways of sort of operationalizing what we mean when we say testing. We could definitely do, especially the thing of looking at the text of the output program, especially when we're thinking about optimization, whether an optimization breaks things. So these are reasonable ways to test, and testing is going to be part of our answer.
I think someone just mentioned it. How do you mathematically prove that a compiler is correct?
I'm so glad you asked. We're getting to that in a moment. So before we get into how do we automatically prove, let's first think about how could we prove just by sort of our sort of standard pencil and paper, right? So one thing that we could do is just stare at it for a really long time and persuade ourselves that it's doing the right thing, right? Like this seems like sort of a weird strategy, but that is actually a huge part of how we usually persuade ourselves that various programs are correct, is we have looked at it and we sort of trust that it is doing more or less the right thing. Maybe we step through line by line. Maybe we use some paper and pencil proofs. So it's not that that's sort of not part of the story. But I think what your question was about was, could we do a formal mathematical proof, a machine checkable mathematical proof? And the answer is absolutely yes. So traditionally, program verification was super expensive, super computationally intensive, actually pretty difficult for programmers to get working. The idea with formal verification is, in addition to the program that you are trying to verify, you write this other program, and the purpose of that other program is to persuade the computer that this program you have already written is correct for some definition of correct. So you first have to think really hard and write down, okay, what would it mean for this to be correct? And then you have to write this whole fancy formal verification program where the goal that it is doing is trying to persuade some kind of proof system that your program is indeed correct. In our context, that would be your compiler is indeed correct. And so for a long time, that was really expensive and really hard to do, and we just could not figure out how to extend that to programs as complicated as compilers. But then, a little while ago, like over the last couple decades, we started to get a lot better at formal verification. We've gotten really good tools for it. And so now we even have a formally verified compiler, CompCert. If you're interested in looking at what a sort of formally verified compiler looks like, look up CompCert. It's really interesting. They, years later, did this really cool test where they were testing a bunch of different implementations of the same programming language in order to figure out, by sort of comparing the answers that they got out of those different implementations, comparing those to find bugs in the various different implementations of that same programming language. And they found bugs in all the implementations except CompCert. The formally verified parts of CompCert had been formally verified. So definitely, formal verification, we had that answer back there as well. Awesome approach. In our context, because formal verification is still fairly hard for programmers to apply, we're going to be doing something a little bit different, which was actually the first answer we got, and I think is a really good answer, which is we are going to go ahead and have a reference interpretation, right? A reference interpreter, a reference implementation, something that we can look at. We are going to be able to persuade ourselves somehow that it is correct, and we are going to say if our implementation of our compiler matches with this reference implementation, then we have persuaded ourselves that it is correct. And so what does that mean about how we should implement our reference implementation? Well, it probably means that we should implement it in a way that's going to be so easy for us to reason about it. We are going to be able to look at it and be really pretty confident that it is doing the right thing, because we want to be able to point to it as this is the source of truth about our programming language. And so what does that probably mean based on the discussion we just had about how we might pick whether we're doing compiler versus an interpreter? Well, probably for our reference implementation, we're going to want an interpreter, because it is going to be a lot easier for us to reason about it most of the time. And so that is the approach that we are actually going to take over the course of this class. We're going to actually have a reference interpreter that we are designing, building right alongside our class compiler. And so you will start seeing the interpreter in that repo that is tracking the course compiler. You will see the interpreter as well. It will usually be a simpler way of reading and understanding what the language is doing. And you will also be doing the exact same approach in your homeworks, right? And so what we will be doing is always checking interpreter versus compiler.
Can we also not just pull like a reference compiler that's like already like popularly used in like public or whatnot, instead of like having to create our own like test compiler? Because then like you make mistakes in both, and they're both like kind of giving each other like bad results, but they're matched up, and so you might think like they're working when there's errors in both of them.
I love this question. So this question was, could we just go ahead and go out there and find an existing implementation of the language and use that as our reference implementation? And the answer is yes, if you are building a language that has been built before. On the other hand, if you're inventing a new programming language, right, maybe you're building this implementation because you just want a more efficient or a more memory efficient, or like maybe there's some reason that you're re-implementing an existing programming language. But a lot of the time, you are trying to implement a language that isn't actually implemented out there in the world, in which case that approach might not work so good. And in fact, that's even going to be the case for us, right? Because we are growing this language incrementally. So there actually isn't, well, okay, I've written one, but there actually isn't a reference implementation out there for our language at sort of each stage. There's various scheme implementations that implement a superset of the things that we are implementing. But yeah, in terms of the specific language that we are implementing, we don't have that match. Yeah, very, very good question. Okay, yes?
Using the reference language approach, can you ever be fully certain that your compiler is correct, or can you only be certain to a certain degree?
With a reference interpreter or a reference implementation, can you ever be fully certain that you're correct? I would argue no, right? So the reason that we think this is a good way to be fairly persuaded is because we know a lot about how to write interpreters and how to write interpreters in a readable way. And so if you look at the interpreter that we are going to be developing, we are going to be doing nothing to make it efficient. We're not going to be doing anything to try to make it do fancy stuff or make the programs work well. Like, we are going to be doing the simplest possible thing, the thing that's easy for us to read. And that is basically how we are going to be making that argument to ourselves that we have landed on something that is correct, right? We are going to look at it. We're going to do the thing of looking at it really hard and being like, that looks to me like it is doing the right thing. And then we're going to see for many test cases, which hopefully we have chosen intelligently, for many test cases whether we're getting the right answer. But there are two ways that could go wrong, right? Like, maybe there's a test case we didn't think to include there. That doesn't look good for us. Or maybe we have, in fact, implemented the interpreter, the reference implementation, in some wrong way. And both of those could go wrong and lead us astray. So if you really, really, really want to persuade yourself that a program is correct, and that applies in this setting, this applies in whatever setting, you want to be using formal verification. So that's why CompCert didn't have any bugs. Other questions? Okay, so I promised that our interpreter was going to be easy to write and easy for us to read and reason about. Let's go ahead and see if that's actually true. Let's try it out. So it's going to have a lot in common with the structure of our compiler. So let's go ahead and take advantage of that. Let's copy this. Let's go ahead and make our new file, interp.ml. Great. Okay, so what are we not going to need? Well, we're not going to need this assembly library anymore because we're not emitting assembly here. We're just trying to get to the value. So let's go ahead and get rid of that. We're still going to need to express when the program that the programmer tried to pile in isn't actually something that we can handle. So let's leave that in. Let's rename this. Let's go ahead and call that interp.exp, right? Because we are now interpreting the expression. Do we want to produce a directive list? I would argue no. Anyone want to yell out what we might want to produce if we are trying to get the value associated with the program? I hear int. I totally agree. I like that. So let's get an int. What's the int that we should get if we have seen a number? I'm hearing n. That sounds good to me, right? That's the number that we see. That is the value that we're interested in. I like it. Let's do n. What about for this addition? What do we want to do here? We certainly don't want to call compile exp anymore. We're not trying to interact with our compiler. The last thing we want is to bring in any bugs that our compiler has into our reference implementation. Hey, let's do the recursive call that makes sense here. So let's recursively call interp exp on arg. And then probably we're going to want to go ahead and add 1 to that, right? So let's go ahead and communicate about what's happening here. Let's interpret it. Then let's add 1 to it. And we're going to do the same thing but with subtraction for what follows. Let's do that. And let's see what happens when we try it. And let's open interp. And instead of compile and run, let's do interp exp. Oops, you know what? We're going to want a little wrapper around this because interp exp, as we can see, is taking an S expression. I don't want to write an S expression. Let's give ourselves a little wrapper. Let interp program string, and let's have it string of int, right? We want to go ahead and actually pop out a string, not an int. Interp exp parse program. So hopefully it's clear what's happening here. We're using our same S expressions library in order to actually parse that string that we'll get as input. We go ahead and call string of int on it, and that's going to give us the output associated with the entire program. So now that we've got that in place, let's try this again. Oops. Let's go back to our interpreter. And instead of compile and run, let's do interp. Great. So okay, I promised that building up our interpreter would be a lot easier than our compiler. Hopefully that feels true to y'all. Hopefully you do feel like you can look at this program and say, yep, looks to me like that is in fact interpreting our language. Yeah?
So why are we recursively calling functions instead of just like incrementing, decrementing right away?
Why are we recursively calling, why are we recursively calling interp exp?
Return like arg plus 1.
Instead of calling arg plus 1. Yeah, so say that arg was num_n, right? Num_n has type sexp. It does not have type int. So if we tried to just add +1, right? If we just tried to add 1 to arg, right? The thing that is in charge of actually getting the value associated with a sub-expression in our language is interp exp, right? That's the thing that we actually need to use in order to get an OCaml value out the other side, in order to get, in this instance, an int out the other side.
That makes sense.
Thumbs up?
Thanks.
Yeah?
How does it know the difference between the two ends that are right next to each other?
How does it know the difference between the two ends that are right next to each other? Is that about these two ends?
Yeah.
So this is actually us naming whatever is actually used, right? Like this is us saying, call this thing n. And then when we want to refer back to it, we use that same name. Yeah. So these matches, right, they're very powerful. We're using them for control flow, but we're also using them for naming. They're combining all of it. All right. So I would say that now we're ready to actually, oh, sorry. I love this. So if we take a look at what is actually happening inside here, right? So what we expect to have inside our list, if you remember when can we actually take a look inside sexp right now? Is this going to be annoying to look at? Hopefully not. Yeah, it actually is going to be kind of annoying to look at. Okay, yeah, this is fine. So you can kind of see what's happening here. But basically what's happening is inside our type, we have 3 ways of constructing an S expression, right? 3 constructors, just the same as all the other types that we've made. We have num of int in this case, we have sim of string, and then we have the list, right, LST, of a list of the same type, right, sort of that recursive thing. And so it's saying that every item that's inside this list had better also be an S expression. And so if we take a look now at interp ML, and we take a look at what's happening here, well, this is one of those lists, right? And so, yep, the first item was made with that sim constructor. We don't know which specific constructor was used to make arg, but we do know that it's going to have type sexp. Thumbs up? Amazing. Okay, so now I think we are ready to use this, our very simple reference implementation. We can use that in order to actually go ahead and do this differential testing that we talked about. I think I did actually introduce its name. I'm so sorry. When we talk about using a reference implementation, we are talking about differential testing. So let's go ahead and make ourselves a diff test function down here. So we're back in our compiler now. Let's do let diff test. What it will take in as input is the examples we will use for actually doing our testing. And that will be a list of strings representing those programs. And then we'll want to go ahead and say let results, my spelling truly is dreadful, let results equal list.map, a function. And what are we going to want our function to do? Well, we're going to want it to run both the compiler and the interpreter on the same input program. So for a given example program, let's go ahead and have it make a pair, right? So this is our syntax for making pairs. Compile and run x interp x. Why compile and run? Well, because we are going to be comparing the outputs, right? We talked about the fact that we might want to compare assembly, we might want to compare that other representation of the program, but in fact that's not what we're going to want here, because there's no reason to think that the assembly that the OCaml compiler is making for our interpreter is going to have anything in common with the assembly that we are making in our compiler. And so we just want to compare those values. Oh, and let's make sure we've actually opened interp so that we're allowed to use it. Interp. So now we should be allowed to use interp. It is not complaining anymore. Great, so now we've got our results. What do we actually want to do it with? So we're going to call that on examples. That's our input right there. And then in, nope, not in there. In list.forAll fun R1, R2. So if we've got this pair coming in, what do we want to do with it? Well, we want to see if the values are the same. Now, you might not be used to using single equals here, right? That's a little bit weird. You're probably used to using double equals when you're doing comparison. For our purposes in OCaml, double equals gives us physical equality, whereas single equals gives us structural equality. You almost never want physical equality. So within this context of this course, you're probably not going to be using that double equals. Get used to using the single equals. And so that we're going to go ahead and apply to results. And that will give us basically whether every single pair, right? We're going to go ahead and do this for all in order to check whether every single pair of compiler input with compiler output, interp output, whether those actually match. So let's go ahead and actually call that on some examples. Let test. What do we want to call it on? Let's do 55. Let's do add 1, sub 1, 30. And let's see how it all goes. So let's open it up again. And let's call test. Okay, great. We got back true, which means that for these two examples, our interpreter and our compile and run did in fact agree. Now, this is not a great implementation of diff test. So for example, we might in fact want to test on programs that we are intending to cause exceptions, right? Something that wouldn't actually be allowed by our compiler. We might want to actually use that in diff test. So you are going to have a better infrastructure for doing differential testing in your homeworks, but this is good enough to get the general idea of what's happening. So let's go ahead and take our 5-minute break. We'll come back together at 4:40. I'm sorry the 5-minute break came so late today. Hello.
Can I ask a quick question?
Yeah.
Are you gonna do like a special topics course in spring?
Yes.
I've seen you've done like a user-centered programming tools
Yes.
design. It sounded very interesting.
I think it's a really nice class. It is mostly for PhD students, so you have to be pretty comfortable doing research, but as long as you're comfy with that.
I mean, I'm a grad student. I haven't done
Oh, you're
research.
fine. Yeah. Yeah, no, I think it's a really fun class.
Yeah, and I was also wondering on like the interpreter versus compiler thing.
Yes.
You combine both the compilation of the OCaml programs and the execution.
Let me
I
go
was
ahead
kind of
and
curious
say.
about that because it made me a bit confused about
Yeah, so
the
we want to
diagrams.
run both in order to actually like get a value out and have it be
Sure.
comparable to the interpreter. But in terms of which part is which, the part that I'm highlighting in purple here,
Yeah.
that is compilation time.
Yeah.
The part that I've highlighted in pink, that's runtime.
Yeah, but the compilation and execution of the OCaml code itself.
That's all happening at compilation time.
Yeah, but why is this one step?
Why is this one step?
Because for executing OCaml code, you first have to compile it and then execute it. And to me, it would be more natural to have them separate.
Oh, to show that the computer's processor is also happening in here,
Yeah,
and that's how we're actually
because
getting
of-
this assembly. Yeah,
yeah.
that would be totally fine.
Yeah.
Yeah.
Okay.
Yeah.
Okay, thanks.
Yeah. Hello.
I had a quick question.
Yeah.
You were just talking about like the differential testing in the homework and wanting to like raise specific exceptions. So like in the homework, one of the examples is like raising a stuck
Yes.
exception, and that takes like a constructor. And I was just wondering, does it matter that the actual like say S expressions are the same between like a compiled and executed version
I
or
see.
like an interpreted version, or is it just that the error, like the assertion or exception, is the same? If that makes sense.
It's hard for me to think of a situation where you would be okay with the expression, the sub-expression associated with the error being different, right? Like in general, the order of operations can matter, right? And so if we're going down the leftmost subtree first in the interpreter, but the rightmost subtree first in the compiler, like maybe we are still figuring out a way to actually have the compiler emit the code for the leftmost first. And so like maybe we figured out some way that's actually going to work for us. But it's really hard for me to imagine, in fact, a case where we would be cool with that.
Right. Yeah. No, that makes sense. Because it's like specifically something I'm like running into for the very end of the homework, and I was like wondering if I'm just kind of like getting away with it because like addition and multiplication are like commutative. Maybe it's like it just sort of happens to work.
Right. But what if we
even though-
replaced our addition and multiplication with a weird addition and multiplication that also prints stuff so that the programmer can see it, right? Like, is that okay?
Right. Probably. Yeah. That's what I was thinking, and that's just why I wanted to like get the opinion to the audit.
In general, we really want, like, we want as much parallelism between, not parallelism, but parallel structure, parallel behavior.
Right.
And we are going to see cases later where that really is going to matter. We're going to run into that in the context of building up the course compiler of, whoop, we did it wrong.
Right.
Yeah.
Okay.
We really want them to match.
Okay. Perfect.
Yeah. If you construct a case where you can persuade yourself that it really doesn't matter, I'm actually super interested about that.
I mean, I can.
No pressure. I know that's a brain teaser.
Yeah. No. I'll think about it. But you make a great point. Like it.
Like that probably indicates that something
very
deeper
hard
is
to-
wrong.
Yeah.
Yeah. Yeah. So,
Okay.
in general,
That's what I was thinking, but I think just having
yeah.
Wait, who was going crazy like 2 weeks ago after the lawsuit? Because look, hella predictable though. They're trying to get people to sell Chrome because they're saying it's a monopoly, but basically they ruled against it because they said we'll use ChatGPT now as we will search. So like it's not a monopoly, people use GPT. So like, and the stock jumped like 20%. Which like, I feel like it's kind of predictable. Like the fact that like they're not going to make people sell like Chrome is kind of crazy. That'd be actually like a crazy decision. Like Steve was trying to buy Chrome. I feel like 40 million. I'm like, bro, no one's gonna sell that shit for 40 million. That shit's Comet's pretty cool. It's interesting. I thought it was 40 million, but like it didn't make sense. They gave him like they like lowballed him. 10 billion.
All right. So going forward, when we add a new feature to our language, when we add it to the compiler, we're going to make sure we also add it to our interpreter. And that's how we're going to persuade ourselves that we are, in fact, correct. We're going to start practicing that immediately. In fact, often, we're going to find out that we can figure out some of the ideas we're trying to work through as we design a new language by first implementing it in the interpreter and then figuring out how to do the same thing in the compiler. So often, we will actually start by implementing it in our reference interpreter and then move on to compiler land. And so basically, for the rest of class, when we start talking about what it means for our compiler to be correct, we are going to mean that it does the same thing as our definitional interpreter. So we want to be pretty sure about it. OK, which brings me to our next topic, extending the language some more. So we are about to add Booleans. So we mentioned the topic earlier of what kinds of values are even available to us right now in the compiler. And we decided that the only thing we actually have is numbers. Right? That's all we've got so far. Right? Even when we're doing our addition, our subtraction, what's coming out the other side of those, also numbers. So numbers are the only values that our programs are working with. And now we're going to go ahead and start adding in some other values. And so we're in particular going to add the new type of Booleans. Our programs are going to start being able to use Booleans. And I think probably some of the programs that we're going to be able to write once we have access to Booleans will have answers that you can sort of predict pretty easily. So I hope everyone is looking at this and saying, well, that should be false, and that should be true. But I want you to go ahead and discuss with someone nearby, what about these two programs? What should be the values associated with those? So there are a bunch of reasonable possible answers here, right? In Python, 0 is like false, and other numbers are like 1. That's fine. In C, there aren't any Booleans. All we have is numbers. So not 0 gives 1, not 1 gives 0. It's just a design decision, right? None of this is handed down from the gods. We get to decide what we want these programs to do. We are building towards a language that looks a lot like Lisp, a lot like Scheme. You probably noticed that from the S expressions. And so we're going to go ahead and adopt the same thing that Scheme does. And in Scheme, there is no such thing as a falsy value, right? The only thing that behaves like false is false, right? That's it. And so, again, this is just a design decision. There's nothing saying that there's one way to do this that is right or wrong. As long as the programmer understands what's happening, it's all good. And so we're going to go ahead and choose to do that. We could have picked something else, but we're going to do this just to match other Lispy languages. It is, in the end, 164 line, going to look quite a bit like Lisp. So if you have used it in the past, you might find that writing programs in our particular language that we're implementing might be a little bit easier. And so we're going to make it look like Scheme's not, which is to say we're going to have this be false and this be false. Because everything that is not true is going to be, everything that is not the Boolean value false is going to behave like true. And so if this is like true and this is like true, then this had better be false and this had better be false. So that's what we're going to do. So far, so good. OK, cool. Now, there are some other things that are going to be a little bit wacky. So what would we like to have, I think, probably like 0 applied to 0? We're probably all guessing that should be true. What about num applied to false? So this is kind of wacky, right? Think about in OCaml. Go ahead and discuss, in fact, with folks nearby. would it make sense to have an operator like num question mark in OCaml? What would we be applying it to? What would we be doing? All right, so hum if you think it might make sense to have this in OCaml. Hum if you think not so much. Oh, okay, some confusion. Cool. Yeah, so I'm going to go ahead and vote for this doesn't make sense in OCaml. So why does this not make sense, right? If we think about all the things we've been doing to persuade OCaml that what we've got in a particular program location is of a particular type, that's the reason, right? We know at compile time that this value that we've got there at a particular location in our program text is going to have type whatever, fill in the blank. And so it doesn't make sense for us to have uncertainty about what type is represented by a particular thing, right? We will know that at compile time. And so this is getting at the idea of, if you've ever heard the terms statically typed language versus dynamically typed language. The language that we are implementing is a dynamically typed language. So at runtime, we are going to be able to figure out what type we're dealing with. At compile time, we're not necessarily going to know. So let's bring back that image that we have of compile time versus runtime. So here's our compile time versus runtime, and we decided that this was compile time, and this was runtime, and this was runtime, right? So if we already know types at this star, right? If we already know types at compile time, that is a statically typed language, like OCaml, right? We can be just looking at our program text. We haven't run the program. Our editor can already, we hover over a particular value, and our editor can tell us what type that is. That is a statically typed programming language. On the other hand, if we can sort of look at a program and not necessarily know what type our thing is going to have, okay, dynamically typed language, like the one that we're implementing. And so having an operator like num question mark makes sense if our language is dynamically typed, like Lisp, like Scheme. Does not make a lot of sense for something like OCaml, because we already know at compile time. Why would we need to check at runtime? So far, so good on compile time versus runtime, static versus dynamic, statically typed versus dynamically typed. Yes? Yes, exactly. So this question was, we are going to want something like num that would check what type we have in the text of the program. We would only want to have that in the text of a program if we were writing a program in a dynamically typed language. Because otherwise, we would already know at compile time what type a particular, if we're looking at a particular piece of the program text and we sort of circle something in that text, we should already be able to figure out, before we ever run the program, what type that thing that we have circled has. And so we would never need something that runs at runtime that checks what type it has, because it's already known, it's already baked into the program. Whereas if we are in a dynamically typed language, that's not known at compile time, right? In fact, often it cannot be known at compile time. There may be no way to find out, in which case we might need to actually run something at runtime, right? Using a language construct that the programmer can actually use. We might need to run something at runtime that checks what type it has. I love this question. Okay, so since we are implementing our language using OCaml, are we ever going to use something like num question mark in the course of writing our compiler or our interpreter? No, right? Like, we have already seen that we can go ahead and do these things where we're saying this, right? Like, I'm hovering over this part of my compiler program and it's telling me what type it has. So we, as the compiler and interpreter writers, will never write something like num question mark. However, The programmers using our language that we are creating for them, right? They may want to write num question mark, right? And so we will, in fact, be implementing a num question mark operation that they get to use in order to check the types of the things in these programs that we are then compiling. Got it?
So type checking will be done in the assembly code that's emitted?
Amazing question. Yes. So this question is, we will check types using the assembly code that is emitted by the compiler. Yes, exactly, right? So if it is happening at compile time, that is something that is being executed using our OCaml program, right? Something that we will have written to do this in our sort of OCaml language program that we're writing. Whereas if it's something that's going to happen at runtime, that means that we have emitted assembly that is going to be able to do it. And so this is an example of something where we are going to be emitting assembly that is going to be able to do it. So far, so good. Yeah, we're really having to navigate that compiler, interpreter, compile time, runtime, all these various sort of mixed up ideas today. OK, cool. So I think we have at least enough time to start putting this in our interpreter. So let's go ahead and try that. Great. Let's swap back to our interpreter. So here we are in interpreter land. We have, so far, only integers. So we could go ahead and do something like sim true maps to 1, but we decided we're not going to do that, right? We really do want to have only false, only the Boolean value false actually behave like false, which means we're going to have something that actually represents that value. So I'm thinking we probably don't want this to be an int anymore. I want you to discuss with folks nearby, what do we want it to be? Discuss for half a minute. I'll give you a hint. What's a trick we've pulled before? All right, I heard people mentioning this. In the past, we might have wanted to create a new type. That sounds good to me. Let's do the same thing again. Let's have a new type value. We can have multiple constructors for it. Number of int or Boolean of bool. That looks OK to me. That seems like something that we might like to have as our return value here in the context of our interpreter. So now we're going to go ahead and just represent those explicitly. What do we want to do here? Well, probably that's pretty clear just from the fact that we know that's going to be a number. So let's go ahead and write number n. OK, but now this is a little bit weird, right? Because it kind of looks as though we've got something coming in and the exact same thing coming out, right? We've got this num n thing, and we're turning it into this number n thing. No, different, right? Because remember that num n has type s expression, right? Just like our program that comes in, type s expression. Whereas this, on the right hand, has type value, right? So we're taking in things that have type s expression, and we're putting out things that have type value. So OK, that's looking good so far. We haven't actually implemented Booleans. Let's take care of our numbers first. So what do we want to have here? Well, we're probably going to do something that looks relatively similar to this. But where exactly do we put that number constructor? Go ahead and discuss for 20 seconds how we will fix this line. so first let's yell out, what type will interp x applied to arg have? Hint, hint. Right, we can go ahead and just read that off our program. Our program says that if we make a call to interp x, the thing we're going to get back is going to have type value. So what do we do if it has type value? Can we just immediately add 1 to it? Yeah, all right. So probably let's do the thing we've been doing where we check if this is the kind of thing to which we can add 1. So let's go ahead and do match interp x arg with, in fact, let's go ahead and give this expression a name just so we can actually refer to it later. So as e, let's go ahead and pop this all inside here. So when do we want to go ahead and do this? Well, if we know that this is in fact a number, then we are good to do something pretty close to this, right? So if it is a number, great, we can go ahead and actually do our addition in that situation. We're going to have to actually apply it to n rather than to this whole call, right? So let's do number applied to n plus 1. That feels good. What if it's anything other than number? Yeah, we don't know what to actually do in that situation. So let's go ahead and say, oops, raise that expression e. And so that's why we bothered to actually go ahead and name it as e. So okay, I want you to real quick, oh, sorry, question.
Are you able to do the matching on the number type in the first match expression?
Are you able to do the matching on the number type in the first expression? Oh, I think I understand the question. Okay, so if we were up here, could we already do the match on the number type here? Great question. So what type does arg have?
Could you match it with number there? Like it's an S expression, right?
Right, arg is an S expression. So if we evaluate add 1n, we're going to get back a value that will be created with the constructor number. But our S expression is simply going to have something that looks like LST, add 1, arg, right? So we do need to actually use interp exp in order to get back the value associated with that expression before we can go ahead and do the match with number, right? Because it's not immediately obvious looking at something like add 1, add 1, add 1, n, right? Like we could look at that and know, okay, well that's going to be a number, right? But in order to actually figure that out, the interpreter is going to have to actually evaluate it and say, okay, yeah, the value I got back was indeed a number. Okay, cool. Discuss real quick. Do we have time for this? Okay, we don't have time to actually fully finish this. I'm so sorry. I keep trying to catch us back up. But what we're going to do is at the beginning of next class session, we're going to go ahead and real quick wrap up adding our new value type inside the interpreter, and then we'll get to add Booleans inside the compiler. Thought we were going to catch up. Thought we were going to.
I just have a question about,
Yeah.
like, I heard a lot of languages are like, their compilers are written in that language. Like, how does
Yes.
that work? It's kind of trippy. Like,
I know, right?
yeah, okay.
Yeah, how do we first
okay,
do it?
Yeah, like, where's like the base case? Or like, yeah, I don't know.
Yeah, so if you remember that very first session when we talked about how Rust, the first compiler for Rust was written in OCaml, and then they had, after that point, a working implementation of Rust. So at that point, they then switched to writing the Rust compiler in Rust. Now, the very first compiler, where did we get that, right? So the very first compiler had to be written in something that could be run directly on the processor, right? So you had to write that in the ones and zeros.
Because the output is like machine code, you can just use that, like actual machine code in the future to run, oh, okay.
Yep.
Okay, that makes
Well,
sense.
and then you get a new, right? Like once you have the Rust implementation of Rust, now you can actually run that in order to get a new implementation of Rust. And now you can run that one. You know what I mean?
I see.
Like we
Yeah,
just
I
keep
see.
going.
Okay, that makes sense.
It's
Yeah,
called
that's more
bootstrapping
concrete.
if you want to look it up more.
Bootstrap. Okay, thank you.
To clarify something about this diagram.
Absolutely.
Not this exact one, but
Maybe one of these
this-
ones? Oops.
Yeah, this one right here. Right?
Amazing,
so is this top section the compiler, or is the compiler the entire thing?
So the purple section is the compile time process.